Alright, in this video we are going to introduce the concept of impedance, and this is a mathematical tool that is going to make our lives easier when analyzing circuits with AC, or alternating current inputs. So we're going to represent that with a symbol, with a circle with kind of a sine wave inside it. So far in this video series, we have only really dealt with circuits with DC inputs, usually coming from batteries, represented by a battery symbol like this, or maybe a circle with, say, voltage label inside it in the plus minus, but without the sine wave symbol. And where we're going with this, with AC circuit analysis in this video series, is really going to be analyzing filters. So you have some, for example, signal coming from a from a sensor, some voltage coming from that sensor that is, maybe it's measuring temperature or position, who knows what physical quantity, and the signal's a little noisy, so there's kind of some, just like you might have mechanical vibrations in a mechanical system, you sort of have electrical vibrations that you want to get rid of. How do you run that through what we will call a low-pass filter that lets the low frequency component of that signal through but kind of gets rid of the high frequency noise? Or the other way around, maybe you're interested in the high frequency component of that signal and you want to get rid of a lower frequency carrier signal, so you run that through something called a high pass filter that lets the high frequency part of the signal through and filters out the low frequency part, so ultimately you can get the part of the signal you care about. That is where we're going to be headed in the next couple videos, but first we need to introduce this concept of impedance, which can get a little confusing because it starts to involve imaginary numbers and things, and you start asking, well, wait a minute, what is an imaginary ohm? You know, I'm a mechanical engineer, we never have imaginary newtons or any garbage like that. Why do the electrical engineers like imaginary numbers so much? And I guess don't shoot the messenger here. Somebody at some point in the history of electrical engineering decided this was an easier way to represent the math, so we're just going to run with it because it's the convention that you'll find in any electrical engineering textbook. And we'll do some hand waviness in the math and just kind of take it for granted, so don't worry too much if you don't remember all the math. We'll do a quick recap in a second, but just remember that if you get a little lost in this video and wonder, hey, why are we doing this at all? This is the goal. We want to be able to build filters to get rid of noise or frequency components of electrical signals that we want to get rid of so we can focus on the parts we care about. Okay, so let's do a very quick recap of some of the math here. So you may remember, if you're just off some cobwebs, something called Euler's identity from a math class you took in high school. So e to the j theta equals cos theta plus j sine theta, and I'm not going to rederive this or anything, and note that we are using j for the square root of -1 here because in electrical engineering, I is already taken for current. So in a math class, usually we use I for square root of -1. In electrical engineering, we use j. And you can also multiply this whole equation by an amplitude, so some constant a, e to the j theta equals a cos theta plus j times a sine theta. And you may also remember that you can use this equation to represent the coordinate of a point in the complex plane where the x-axis is real and the y-axis is imaginary. We have some angle theta and some amplitude a, so you can represent the location of that point in either polar coordinates or xy coordinates. So all of that is just to set the stage for, at some point, somebody in electrical engineering, I guess, decided they didn't like writing out sine or cosine terms, so that they were going to represent a sinusoidal voltage source, Vs, with the real part of this equation, but represent it like this and not bother writing out the real. So this is kind of just a definition, just implied. You can go look up a textbook that will derive the whole thing and explain where this came from. We are just going to take it for granted that instead of writing our voltage sources as something times sine or cosine, we're going to write them like this: amplitude times e to the j omega t. Where, again, that just means we have a totally real sine wave with amplitude a and angular frequency omega that we are representing with this notation. There are no imaginary volts involved here at all. This is a totally real excuse me, I'm recording this video while getting over a cold. totally real voltage. This is the convention. Just take it for granted, where again, J is the square root of -1. Omega is the angular frequency in radians per second. A is the amplitude of the signal. And of course, if you want to convert to hertz, you have F equals 1 over 2 pi times omega. So that's in hertz. And a quick example, why would you care about AC or alternating signals like this? Wall outlets, right? Anything you plug into a wall outlet, depending on where you are in the world, it's going to be a different frequency or potentially different amplitude, but as opposed to battery-powered circuits, wall outlets have alternating current. So again, take this definition for granted. Don't worry too much about remembering all the Euler's equation stuff and the derivation of that you may have done way back in an algebra or trig class or whatever. We are taking that for granted for this video. And next, we are going to define a new thing called impedance. And you might hear this term or see it in a data sheet or something and go, okay, what exactly is impedance? It has units of ohms. Why don't they just call it resistance? And we'll talk a little bit more about that in a minute. We are going to use the variable Z to represent impedance, and we are going to define it as the ratio of voltage to current. And if you remember Ohm's law, V equals I over R, and you rearrange that to solve for resistance, R equals V over I, you might say, well, wait a minute, isn't impedance just resistance? And as we will see in a couple of minutes, for a resistor, that winds up being true. But remember, we also have capacitors and inductors that we have seen in previous videos, and these don't have resistance. They have capacitance and inductance. So what we'll see is that we can also define this ratio of voltage to current for capacitors and inductors, and sneak peek, for capacitors and inductors, that impedance is going to be frequency dependent. If you remember, again, from the previous videos in this series, we have differential equations that describe the behavior of capacitors and inductors. So there's a time component to their behavior, unlike Ohm's law, which is a purely algebraic equation with no derivatives in it. So what we will see on the next couple slides is that we're going to derive the impedance for both a resistor, a capacitor, and inductor. Once you have slogged through that derivation once, you don't need to do it again. You can just take for granted that you have the equations for the impedances of those three parts, but we kind of want to show the process you go through to arrive at that in this video. Okay, so we're going to do this first for a resistor, and this one seems a little trivial, but I think setting up the process with the resistor will help explain how we're going to do this for inductors and capacitors. So we have our AC voltage source, Vs, just connected directly to a resistor R, and we want to know what is the impedance of this resistor. What is ZR? And we have defined impedance as equal to the ratio of voltage to current. And we know that our voltage source, as we wrote down on the previous page, Vs is equal to AE to the J omega t. So we have AE to the J omega t. And we know that Ohm's law applies to a resistor, so we want to solve for I here. I equals V over R equals A E to the J omega t over R. So if we plug that in for I, we have 1 over R times A E to the J omega t. The A E to the J omega t's cancel. The 1 over R flips up top. And we get just ZR equals R. So the impedance of a resistor is just equal to the resistance. Nothing super surprising or weird there. Again, we kind of already knew that. We know how resistors work. We know that Ohm's law doesn't have any time or frequency dependence to it. But we are going to follow that same kind of procedure for a capacitor now and look at the interesting result we get for a capacitor. So same setup, we have our AC voltage source, and note that there's sort of the weird thing there where we use the abbreviation AC, which stands for alternating current. So when you say AC voltage, you're really saying alternating current voltage. I don't know why there isn't a convention to call something AV, for example, alternating voltage. Again, I didn't invent the field, so don't get mad at me. Kind of weird. But anyway, we have our AC voltage source which is Vs by our convention for how we're writing this, Ae to the j omega t, applied to a capacitor C, and we want to know what is the impedance of this capacitor, the ratio of the voltage across the capacitor to the current through the capacitor. Now, we know that since there are only two components in this circuit, the voltage across the capacitor has to be equal to the source voltage. So we can rewrite that as Vs over IC, the current through the capacitor. We know that our voltage source is equal to Ae to the j omega t over the current through the capacitor. And here we're going to write down our capacitor equation. Remember, capacitors are not resistors. Ohm's law does not apply to them. But we have the equation that the current through a capacitor is equal to C times the derivative of voltage across the capacitor. So we can plug that in here, Ae to the j omega t over C dVc dt. However, remember that the voltage across the capacitor is equal to the source voltage here. So dVc dt is the time derivative of the source voltage, which is derivative of Ae to the j omega t. Taking the derivative of E, this term is going to come out front, so that is going to be aj omega e to the j omega t. Again, we're not doing a calculus review here. I'm just assuming you kind of know how to take that derivative. If not, you can just take my word for it. So now we're going to plug, this was just the derivative term in there for the derivative. This is a e to the j omega t over c a j omega e to the j omega t. The a's are going to cancel, the e to the j omega t's are going to cancel, and we are going to get 1 over c j omega for the impedance of a capacitor. And notice that now we do have a frequency-dependent term. The omega did not cancel out. So I'm going to rewrite that down here since we kind of ran out of space. The impedance of a capacitor is equal to 1 over c j omega. So note that it's inversely proportional to capacitance. As capacitance goes up, impedance goes down. And let's look at what happens in the limits for omega. So as omega approaches 0, or we have a DC or constant signal, then ZC, the impedance of the capacitor, is going to approach infinity. And in other words, if you think about impedance kind of like resistance, that's saying as the frequency of the source goes to 0, so you pretend you just replace this with a battery, you have a constant source instead of an alternating source, then the impedance or kind of effective resistance of that capacitor goes to infinity, which is like having an open circuit. And if you think back to what we learned about capacitors earlier, we said that in steady state, when things are not changing, a capacitor does act like an open circuit, which is again sort of the same as saying something has infinite resistance or infinite impedance. And we can also see that from the equation for a capacitor. Remember, if we're in steady state, our derivatives are 0 and nothing's changing. So if this derivative is 0, the current has to be 0. So now we just kind of have another way of expressing the same thing. But what's interesting now is that we can also see what happens when the frequency goes to infinity. So we're not just limited to this DC steady state case anymore. So when you have a signal that's getting higher and higher frequency, oscillating faster and faster and faster, how does a capacitor behave? And in that case, if the denominator of this fraction goes to infinity, we see that the impedance of the capacitor is actually going to go to 0. So in this case, the capacitor is going to act like a short circuit. If you have an extremely high frequency signal across a capacitor like this, it's like the capacitor just isn't even there at all. Which is, again, something before we've thought about things in how things behave in steady state with essentially a 0 frequency signal. We haven't thought about this high frequency limit. And this is going to be interesting when we go to use capacitors, resistors, and inductors to build filters in future videos. So again, we knew about this before, kind of in DC steady state, capacitor acts like an open circuit, but now we know that for high frequencies, the capacitor acts like a short circuit. If I can remember how to spell frequencies. Okay, we are kind of out of room on this slide, so let's go ahead to the next one, and we are now, again, going to go through the same process for inductors. So if you want to pause the video here, you could try and figure this out yourself by following the same procedure that I did for the capacitor. Again, you'll have to go look up the equation for an inductor as opposed to the equation for a capacitor, but then you can follow the same process. Pause it and see what you get, or you can cheat and just keep playing and watch me derive it. So, same setup for an inductor. We are going to have our AC voltage source connected to an inductor with inductance L. Our voltage source is represented by AE to the J omega T. We know that, or we want to solve for the impedance of an inductor. ZL equals V voltage over the inductor over current through the inductor. We can substitute in our voltage source, AE to the J omega T. We are now going to need our inductor equation. We know that the voltage across an inductor is equal to L di dt. So we can take the integral and write that the current through the inductor is equal to 1 over L integral of the voltage, and go ahead and plug that in here. So 1 over L integral of the voltage, which again, the voltage across the inductor here must be equal to the voltage of the source. So integral AE to the J omega T, and that is going to come out to, if we take that integral, which again, if you don't remember how to do it at this point, you're just taking my word for it, 1 over L times 1 over J omega AE to the J omega T. So again, we have the AE to the J omega T terms cancel, and this whole term in the denominator of the denominator is going to flip up to the top, and we get that the impedance of an inductor is equal to LJ omega. So similar to what we had for the capacitor, except this time the impedance is proportional to both the inductance and the frequency instead of inversely proportional to them. So we can look at, again, the limits of behavior as frequency approaches 0 or frequency approaches infinity. As frequency approaches 0, the impedance of the inductor is also going to approach 0, so it acts like a short circuit, which again is consistent, again, if I can spell, with what we saw before, whereas we approach steady state, so derivatives are 0. If the derivative of the current is 0, then the voltage drop across the inductor is 0, so it acts like a short circuit. But as the frequency approaches infinity, the impedance of the inductor is also going to approach infinity. So there it is going to act like an open circuit. And I think this is where it helps to use that mechanical analogy to think of an inductor as a mass, and kind of the very rough analogy here between mechanical and physical systems where current behaves like velocity and inductance behaves like mass. If you apply a very, very high frequency alternating force to a mass, right? So you keep oscillating the direction you're applying a force to this mass, then it's never actually going to have time to start accelerating in either direction. It's just kind of going to vibrate back and forth in the same spot, but it's not going to, as opposed to the steady state case where you apply a constant force to a mass and it's just going to accelerate in a single direction. Kind of the same idea with an inductor here. If you just keep applying a higher and higher frequency signal to an inductor, then it's going to act like an open circuit. And this becomes relevant later when we talk about motors and why motors take time to start up. Just think of a motor like having mass. It takes time to accelerate a mass. Well, it takes time to start up an inductive load like a motor because, again, at high frequency, if you have an instantaneous or very fast change in something, it's acting like an open circuit. So to summarize all three of our impedances that we learned there, we have the impedance of a resistor is just equal to R. The impedance of a capacitor is equal to 1 over C J omega. And the impedance of an inductor is equal to L J omega. So there is no frequency dependence for the resistor, but we do have frequency dependent impedance for the capacitor and the inductor. And one final note that is going to be useful in the next couple of videos is that we can treat impedances like resistance when it comes to the rules for dealing with them in series and parallel. So if you have two impedances, Z1 and Z2, in series, the equivalent impedance is going to be Z1 plus Z2. And if you have them in parallel, Z1 and Z2, then the 1 over the equivalent impedance is going to be equal to 1 over Z1 and Z2. Oh, sorry, plus 1 over Z2. The difference here being that before we just did this for resistors, this now applies whether either one of these parts is a resistor, a capacitor, or an inductor. So you can mix them. You can have a resistor in series with a capacitor. You can have an inductor in parallel with a capacitor, or all three in parallel with a resistor, and so on. And you can solve for the equivalent impedance of this combined circuit with different elements. So again, it's not the same as, oh, I have two resistors in series, what's the equivalent resistance? I have two capacitors in series, what's the equivalent capacitance, and so on. This equation is agnostic to what these elements are. They can be capacitors, resistors, or inductors. That allows you to find the equivalent impedance of the circuit, and that is going to be useful when we start analyzing filters, which we will do in the next video.